This is the first video that goes along with Chapter 1 entitled An Overview of Computers and Programming. The objective of Chapter 1 of your textbook is to review computer systems, talk about program logic, talk about the program development cycle, talk about what pseudocode is and how to write it, talk about flowchart symbols and how to draw flowcharts, use something called a sentinel value to end execution of your program, talk about different programming environments, development environments, user environments for programming, and then talk about the evolution of programming modules over time. Computer system should be reviewed. You should have talked about this in CIT105 and CIT110. It's just all the components of a computer that are required to process data. The hardware is the actual equipment, the chassis, the CPU, the power supply, the hard drives, the memory, etc. The software are instructions to the computer that tell the hardware how to function. Programs are a type of software, and they are written by programmers, and that's what we're to learn about in this class. Application software would be things like Microsoft Office, Excel, other spreadsheets, payroll, games, etc. The term system software describes the operating system. Most of you are probably familiar with Windows, but that also includes Linux and Unix, Mac OS X, etc. Computer hardware have three major operations that we need to be aware of. We input data. That data, when we talk about data types, we'll see that that's text, numbers, images, sounds, etc. It performs calculations, which is referred to as processing. These are done by the CPU, the central processing unit, again, that you should have learned about in previous classes. Output is sending information out to something. That something may be a printer. It could be displaying information on your monitor, or it could be writing it to storage devices. And those storage devices could be hard drives, flash drives, CDs, DVDs, Blu-rays, etc. A relatively new concept would be writing it out to the cloud. So something like iCloud, or something on Amazon Web Services, or many of the other cloud service providers. There's a section of your book later that talks about cloud services. When a programmer writes a program, they do it in a particular programming language. Your first homework, not your first, one of your first homework assignments had you go out and learn about assembly language and high-level languages, what is a compiler, what's an interpreter, what's a scripting language, etc. But regardless of which of those you're using, you as the programmer are going to write a set of instructions that's referred to as program code, or simply just code. The process of doing that is referred to as coding the program. Some examples are Visual Basic, C#, C++, Java, Perl, Python, etc. In this class, we'll probably primarily use some form of BASIC. Later in the semester, we may look at little snippets of codes or writing other programs as I see appropriate. When you learn about a programming language, one of the first things you have to do is learn about the syntax of that language. The syntax is basically the rules governing word uses and punctuation. So, we have proper English. There's rules to form a sentence that make up proper English, etc. Syntax is what words or what type of information needs to appear. Some programming languages, for example, at the end of every line, you have to have a semicolon. That would be one of the syntax rules for that language. If you make mistakes and misspell keywords or put additional information or not enough information or not the type of the information that was expected by the compiler, that's going to be referred to as a syntax error. So after you write the program, the first time you run it, if you have syntax errors, you then have to go back, look at your program, and correct those until the program is syntactically correct. That means it contains no syntax errors. Computer memory, RAM, random access memory, is where programs or data that are being processed by the CPU must be stored. So your program will be in computer memory. The data that it may be working on will be stored in memory as well. When we talk about memory in 111, you should have learned about volatile and non-volatile memory. Volatile memory means that if you remove power and reapply power, the contents are lost. Examples of that, as are being pointed out in the slide, is RAM on your computer. Non-volatile memory is memory that you can remove the power, reapply power, and the contents are still there. Kind of the main example of that would be a flash drive. You unplug it from the computer, plug it back in the computer, and the contents are still there. Those are also referred to as permanent storage devices. Compilers and interpreters are basically what prepare your code to be run. A compiler actually takes source code and converts it into binary, sometimes we're called machine language, because ultimately that's all the computer understands is a bunch of ones and zeros. The compiler, as it looks at your code, makes sure that it's syntactically correct. If it is not, it will give you error messages that you need to correct. If your program is syntactically correct, then it will compile it into an executable that can be run on the computer. Once you get to that point, you run the executable. If any input is requested, you can type that in and it will be accepted. There is usually some processing that occurs, and then there may be times that you output information, a lot of times to the screen, but sometimes it might be to a data file on your computer so that the output can be looked at later. And the program may actually have a combination of those. As I stated on the last slides, if you have syntax errors, your program is not 100% syntactically correct, it will not compile it into an executable, and therefore you cannot execute it. Logic errors, basically the program runs, but it doesn't function correctly or give the correct output. A really old example of this I heard was there was a program that was written to calculate missile trajectory. You know, if you shot a missile with this much force at this angle, it was supposed to plot the path. The program got run and the output was sent to the person running it, and it ended up being a semi-truck full of printouts when really it should have just been a couple of pages. And the reason was the person, instead of putting gravity in as a positive value, they put it into as a negative value. So instead of the missile being shot and coming back to Earth, it curved upwards into outer space. So the program ran, it generated lots of outputs, but it had a logic error. We refer to logic as just being the set of instructions that have to occur in a particular order for your program to function. A variable is a named memory location. So ultimately, memory locations have numeric values, but it's a lot easier for us to say x equals 2 times y. And if that's the case, x will be a memory location, y would be a memory location, and our compiler would turn those symbolic names or those variable names into actual memory locations, which would be needed when the program is executed. The program development cycle is basically the way you go through and write programs. And, you know, this applies to writing programs for this class, except maybe the very last point or a couple of points. But first thing you do is you have a problem. You may talk to somebody. They may tell you what needs to be done. I, as your instructor, may explain a problem to you. Then what you need to do is figure out the logic. What information do you need to get? What calculations do you need to perform? What output do you need to generate, etc. Once you have that done, well, that's typically done with pseudocode or a flowchart. Once you've done that, then you code the program in whatever language you're going to use. As I said earlier, we're probably going to use BASIC. And then you use software, which for a high-level language would be a compiler. For a scripted language would be an interpreter. And basically what that does, there's a slight mistake here. A compiler will translate the program into machine code. The interpreter might convert it into something called intermediary code, but it will not be machine language. Once your program compiles, then you test the program. You execute it, you type values in, see if you get the results that you anticipate. You might try running it 2 or 3 times with different sets of input. You might, do things like ask somebody how many dollars does something cost, and if they don't put in a numeric value, then give an error because you were expecting a numeric value. You may see if your program handles that correctly. If this is a program that you're writing for a business, let's say, then you would do something called put it in production. You would put it where your end users could get to it. You might give them some training on the program or some documentation on the program. And then over time, you would maintain the program. That's adding additional features. If somebody discovers a bug, they may report it to you, and you would need to go back and look at the logic of your program and the code of your program and correct that so that it worked correctly. This is basically a circle. Maintaining the program means understanding new problems or new parts of the problems, planning the logic, writing new code, etc. So a lot of times, for a program in class, you're going to stop where it says put program in production. You're going to turn it in for grading. But in real life, this circle goes on and on and on for as long as the program is in use. Couple of terms that I mentioned. We talked about users and end users. These are who you're writing the programs for. If they don't like the way the program works, or they don't think it's obvious enough, or you need to change it, you will interact with the users to do that. Documentation can kind of come in 2 forms. Here it says supporting paperwork for a program. The documentation may be documents that talk about the program itself. Then there may be additional end-user documentation that tells users how the program is supposed to work from their perspective. So you have different types of documentation. A lot of times when you talk about programming, you talk about algorithms. Algorithms are a sequence of steps that you follow to solve a problem. So that's basically you thinking out the problem and how to solve it. Helping you come up with the algorithm, we have pseudocode, which is a semi-English-like language to describe what needs to happen. After you have your pseudocode written, you would go back and code it into whatever particular language you plan to use. Flowcharts are pretty much the same thing, just that they're graphical in nature. There's also things called IPO charts, input, processing, output, and then there's TOE charts, which are task, objects, and events. In this class, we'll be using flowcharts and pseudocode. Desk checking is basically going through your program, looking at the logic to make sure you haven't overlooked anything prior to setting down and starting to code in whatever particular language you are using. There are hundreds of programming languages available. They all have different features. Some of them are considered much more easy to learn than others. Basic is relatively straightforward. I said that's probably what we will use for most of the things that we do in this class. Then there's other very powerful languages such as C++ or Python that are very common and that you could use, but there literally are hundreds of languages available. Here they say experienced programs can successfully combine logic planning and programming code into one step. Yes, a lot of times people do that, but in the beginning, when you're learning, using flowcharts, using pseudocode will help you kind of isolate solving the problem. And then once you've solved the problem, then you can deal with coding it. And if you're coding in a language that you're not super familiar with, then separating those two parts is usually much better and less frustrating on you as a programmer. A translator program is a compiler or an interpreter, and basically what it does is it changes your high-level programming language, such as C++ or Java, into low-level machine code. Again, a syntax error is a mistake in syntax, which is a mistake in the grammar rules. If you get one of those, you correct it, you recompile, hope you don't get any more syntax errors, but if you do, you look at the new syntax errors and deal with those. One thing that it might be early on to point this out, but if you run a program and you get 100 syntax errors, you should really concentrate on the first 2 or 3 and then try to recompile your program, because a lot of times one syntax error, forgetting a semicolon, forgetting to close a double quote, etc., may generate lots and lots and lots of syntax errors. For example, in that program when I said it outputted 100 syntax errors, you might really only have 2, and if you corrected the first ones, the others would go away. This is basically showing you a flow chart. You write and correct the program code, you compile it. If there were syntax errors, you go back, you write and work on the code some more, you compile it. Once you get out of that circle and have all your syntax errors gone, then you execute the program. The program takes data that the program uses. That data may come from a user, it may come from a file, and then any output that is generated, for example, maybe output to a file on a hard drive, is stored. A logic error is syntactically correct, but you calculated it wrong. The example I gave you before, the missile trajectory, that program ran, it generated way more output than it should have, but it executed, it was syntactically correct, but the programmer had a logic error. He put a value in with the wrong sign. Testing the program, as I mentioned earlier, is just running the program, inputting some sample data, and see if the output that you get makes sense. If not, you go back and correct it. This process of finding programming errors and even, I would say, syntactical errors is referred to as debugging. You're trying to eliminate all the bugs or problems in your program code. Also, when you write a program, especially if it's a non-trivial program, you shouldn't run 1 or 2 test cases and go, yeah, my program works. You really should run many, many, many test cases, putting valid data, invalid data in, etc., making sure that your program does everything that it should do. Putting the program in production, as I mentioned earlier, is just putting it out there for the users to have access to and run it. Depending on the program, from the time you start coding it to the time you put it in production, might be a day, might be a few hours if it's a fairly simple program. If it's a more involved program, it might take you weeks or months. And if it's something, for example, like PeopleSoft, which you all use to check your grades, register for classes, pay your bills, etc. That might even take years to write. So that really depends on the program's purpose and the scope of its functionality. Conversion is taking an old set of programs and putting a new set in place. When they talk about a conversion, they talk about something major, changing programming languages, greatly changing the functionality of the program, etc. After your job goes into production, you may have maintenance. A lot of times when you get a programming job, you will come in and you will be, replacing somebody that has left the company or somebody that has retired. They had a set of programs that they wrote and maintained. Your first job might not be writing new programs. It might be maintaining programs written by other people. If you need to make changes to existing programs, then you would just go through the development cycle and, understand the program, plan the logic, code it, compile it, debug it, etc. Sometimes programs go years without needing updates. Other programs need kind of continual development. It just depends on what the program does in your environment. Pseudocode is an English-like representation of the logical steps that take to solve a problem. I know that you've already had several assignments in your homework that deal with pseudocode. A flowchart is just a pictorial representation of the same things. Some people like pseudocode better, some people like flowcharts better. They both serve the same purpose. I don't know. I personally probably lean a little more towards flowcharts, but that's really a personal thing. Here on slide 19, we see an example of pseudocode. Basically, the problem is double a number. So the logic you need to understand there is we get a number, we multiply it by 2, and then we tell the person what it is. So we have the terminals start and stop. That tell where the start and the end of our program are. Where our program is. We input a number and we call it my number. So this would be reading a number from the user. You would then set your answer to the number the user entered times 2, and then you would output my answer. This is a fairly straightforward program, but they want to start easy. There are some things like, for example, when they say input my number, in real life when you write a program, you need to tell the user what you're expecting, like please give me a number to double, and then input the number. So there may be things that you do outside the pseudocode to improve on just the statement, input my number. This is a quick reference that is included in your textbook that basically tells you some things. They don't talk about module yet, but a module is where you group some logic off to the side that you may use over and over again. You have a module name and a set of parentheses that's going to have something called arguments in it. They will execute and at some point return execution back to your program. Each program statement should do one thing. You shouldn't group them together and say things like get a number and multiply it by 2. You should do things in discrete steps. Each program statement typically appears on a single line. Most languages allow you to put multiple statements on a single line, but that's not considered good practice for readability. There are times that your information will not fit on a single line and will be continued onto another line, and all modern programming languages allow you to do that. You have rules. Program statements, program keywords typically appear in all lowercase. And here it says there's no punctuation used to end statements. That is when you're writing pseudocode. As I mentioned earlier, when you convert this to a programming language, there may be, quote, punctuation that is used. For example, in C and Perl and those types of things, typically you need a semicolon to designate the end of the statement. Flowchart is basically a picture. They say connect shapes with arrows. Most people are going to say that represents the flow of logic through the program. If you're going to input something, it's in a parallelogram. If you're going to process or manipulate data, that appears in a rectangle. So here they say set my answer equal to my number times 2. So you're basically telling what processing or what calculation should be taking place. If you need to output something, you would do that in a parallelogram as well with the keyword output, in this case, output my answer. And then, as I mentioned earlier, you have terminal values, which are start and stop for the time being. We'll see how that happens with modules when we get to modules. Here's a very simple flowchart that matches up with the pseudocode we saw a moment ago. The program starts, it gets a value from the user, it multiplies that value by 2 and stores it in a variable called my answer, and then my answer is outputted to the user, and then the stop indicates that your program is done executing. The program that we just saw only works for one number. If you need to double another number, you would need to re-execute the program. One thing to mention that I haven't, and I don't know if your textbook does or not, is once you compile a program and have an executable, if you need to run that program, you just run the executable over and over and over again. You don't have to recompile it each time the user wants to do something. The only time you would need to recompile it is if you were changing the code, adding some functionality, or fixing a bug, for example. But if you wanted to double 10,000 numbers, running the program 10,000 times, typing the number in, and getting it outputted is not going to be very pleasant. Also, it's not going to be considered good programming to just copy and paste, input, calculate, output, copy and paste that 10,000 times. A better way to do this is to use something called a loop. And what a loop is you have a set of sequences that you would like to execute over and over again. So in the previous example, we input a number, we double it, we output the number. We can put something around that called a loop that would just keep going back up to the top, go to the top, and do it some series of times. Now, if we just put a loop and said, here's a loop, input a value, double it, output it, it would run forever. A program that runs forever is considered an infinite loop. Sometimes you write programs as an infinite loop, knowing that when the machine shuts down or when the system administrator kills it, it will stop functioning. But typically, infinite loops are logic errors. You're trying to terminate execution of the program, and it doesn't function correctly. So here they're showing you what not to do, which is input a number, double it, output it, input it, double it, output it, etc. 10,000 times. If you had to write the pseudocode for that, you wouldn't be real happy. If you had to write the actual code for that, you would not be real happy. So a better way to do this is, or the first thing you might do is say, okay, after I output the answer, I want the flow of the control to go up right before I input my number. So this will input a number, it'll double it, it will output it, and it will do that forever. So you have an infinite loop. So when you did the 10,000th number, it would want the next one and the next one, and it would just keep running. So, good idea, but you create something called an infinite loop. The way you get looping without having an infinite loop is by making a decision or testing a value. And the decision symbol in flowcharting is a diamond. And basically, you're asking a question. Is my number equal to 0? So what they're setting up for here is something called a sentinel value. So basically, you tell the user, type in as many numbers as you want, and I'll double them and tell you what 2 times the number is forever until you type in 0. 0, everybody should know 0 times 2 is 0. That's not a number that you would probably be entering into a program. So this was a value chosen to say when the user tells me they want a double 0, they really mean they want to terminate execution of the program. And by setting a value to indicate the end of execution of a program, that value is called a sentinel value. You're basically watching for a particular value to stop execution of the program or to terminate the loop. If you're reading your numbers from a file, maybe you've written your program in such a way to take a file from the user, and if it has 50 lines, then double all the values on the 50 lines. If it has 100 lines, they would want to do all 100. When it tries to read another value from a file, and you've already read all the values from the file, you get something called end of file, or EOF. And basically that says, okay, there's no more data in this file. And you can basically say something while not end of file, execute this loop. And when you do hit end of file, then you would jump out of the loop and continue on in execution of your program. So basically what they're doing here is they're asking, is my number 0? Yes, stop. If it's not, then double it and output the user. So that goes through, and not the best way to solve it, but here in the beginning while you're learning about pseudocode and flowcharts is perfectly acceptable. If you're reading numbers from a file, you can say, did I hit end of file? If so, then terminate my program. So with what we know right now, what little we know about pseudocode and flowchart, this is an acceptable thing to do. But when you learn about syntax of programming languages, it'll be structured a little bit different. Okay, there are lots of different ways that you can program. You can simply go into a text editor and type in a text file that has the code of your program and save it and execute it. A fancier type of thing is called an IDE, that is an integrated development environment. Basically, you're in a program. That program allows you to edit. It might even do visual, real-time syntax checking for you. It might automatically substitute in values, like if you start a loop, it'll automatically put the end of the loop in for you. That type of thing. You can compile from within the IDE, maintain code, etc. So those are the 2 ways as a programmer you might interact. I didn't really, I've been programming for decades. And typically, I'm going to go in and use a text editor and prefer that over an IDE. And that may just be because when I started programming, there was really no such thing as an IDE. Those came later. But I've really never liked IDEs up until a few months ago. I was taking some training on Python, and they used a IDE called Aptana Studio, and it's actually really nice, and I like it. I might use it for traditional programming languages, but what I really liked it for was writing HTML and CSS. But you can write in a lot of different languages using Aptana Studio. From a user perspective, they may have a command line interface, which just looks like a computer screen that has text on it. You type things are outputted to you. But these days, most people expect a graphical user interface, which is either referred to as a GUI or a GUI. And basically, that's your nice point and click drag and drop type environment that most people are used to these days. Depending on what you need to provide your user with may impact what language you choose to write in and how complicated or more involved the program is going to be, so that the user has that nice graphical user interface. This is Visual Studio C#. It shows you the code. Notice that keywords and variables and string constants are highlighted in different colors. So, it's a little bit more point and click and has lots of features that are available to you above and beyond what you would have in Notepad or TextEdit or whatever editor you use. This is a command line environment. It just types out enter a number. The user types 13 and your program says 13 doubled is 26. They would typically get the command prompt back if this is a one-shot program. If you were doing a loop, then it might say, please enter a number, and just repeat this over and over again until you entered the appropriate Sentinel value to terminate execution of the program. This is a graphical user interface. You type a number in, you hit return, and it says 14 doubled is 28 in this case. You could probably go back up, type a new number in. If the program did not terminate, hit return, and then it would give you that value and tell you what it was doubled. So people have been writing and using computers since the 1940s. Back then they coded basically in ones and zeros. Then assembler came along, and then higher level languages came along that are easier to understand and had a lot more features like subroutines and modules, things that we'll learn about over the course of this class. The two major paradigms that are used by programs are procedural and object-oriented. In the beginning, when you first start learning programming languages, you're typically taught procedural programming. That's what we'll start with in this class. Where you have procedures or subroutines that you might call to develop code, and it goes through. Object-oriented programming we will discuss a little later in the semester, but basically instead of thinking about the steps that are needed to accomplish a task, you think about things or objects. You might have an object called a person. That person object will have an age. It may have a home address. It may have a social security number. It may have a pay rate. And then you have instances of the objects. Each instance of an object would represent one person. So I might have an object that has that information for myself, and then there would be another object which represents you and your information. And then these objects interact and with each other to perform as a system or a program. It's a whole totally different way of thinking, but typically object-oriented programs are much more featureful and are prone to less errors when they're executing. So that finishes up Chapter 1. You'll have some homeworks. You already had some homeworks assigned, and then I will develop another lecture or lectures that cover Chapter 2.